Let's talk now about how we actually came to realize what our own Milky Way looks like. Here's, for example, the map of the Milky Way, our galaxy, as it was known and thought of in 1785. So this is a map that was published in a paper in that year by the English astronomer William Herschel, and it's based on work that he and his sister uh, pursued together actually at their home observatory. So, work where they presented this map of the Milky Way Galaxy. So what they've done was they counted and located in the sky all the stars in the various parts of the sky, right? So they realized, okay, our solar system lives inside something. So let's look around, and here's what they found. And it says here that's actually far from reality, and the reason is obviously the fact that all these measurements, this is not the entire structure or shape of the Milky Way, because they were only looking at whatever was visible at optical wavelengths, wavelengths, and we know that interstellar dust. Look at this. That's like kind of like one idea, right? Interstellar dust blocks our view of distant stars, and that led them, the scientist William Herschel at the time, leading him to the erroneous idea that the sun is at the center of the galaxy, which we know now this is actually not the case. If this is the disk of the galaxy, we have the galactic center. Here we are, the sun and its planets orbiting around it. They're about halfway between the galactic center and the edge of the galaxy, the Milky Way. Here is an illustration of the techniques that we use nowadays, and we've used, say, for at least 50 years now, in order to map our galaxy. So it says here, Milky Way's structure. We have here the so-called H1. This is atomic hydrogen, right? Every time we see that H, that's what it stands for. So we actually map the existence of atomic hydrogen, like how much atoms of hydrogen exist out there, and we can actually do that in at certain wavelengths, 21 centimeters. So this is the wavelength in radio. So it's mostly radio observations that the H1 clouds, or the atomic hydrogen clouds, how they reveal basically the structure of our galaxy. So let's start with this. This is S for sun. This is where we would be. This is our solar system, so we're one of the planets. So somewhere in that red dot, that's us, and we look within the plane of the galaxy, right? So that's our line of sight. We're looking that way, and from our position at point S, the hydrogen clouds at different locations, shown here as 1, 2, 3, and 4, along our line of sight, they're moving at slightly different speeds relative to us. How do we measure the speeds? We make Doppler measurements. Right, so we basically see that clouds 1 and 3, they're approaching us, because instead of seeing that hydrogen emission at 21 centimeters, we see that blue shifted, right? And it's that amount of shift that is going to give us that component that is along the line of sight. Look at that, right? So we're gonna see this V1 if you want and V3. And another example is, for example, cloud 2, right, is approaching us at a much faster speed, right? So if you do again the projection on the line of sight, this is much larger speed, okay, larger blue shift. However, cloud number 4 is neither approaching nor receding, because especially along the line of sight there is no shift, there is no motion, right? So basically this cloud number 4 is moving perpendicular to, so this is V that is perpendicular to the line of sight, right? Okay, so this is the technique. Now look, for example, at the map on the right. Okay, so we have a hydrogen 1, or the atomic hydrogen map of our own galaxy. This is how it looks like, and you can almost distinguish basically the spiral arms. And it says here, this is where the sun and its planets are. So this map is constructed from radio telescope surveys of the Milky Way, of basically everything out there, of 21 centimeter radiation. And the map definitely suggests a spiral structure. And you might notice this wedge-shaped region at the bottom of the map, and this is basically no reliable data. Why do you think that is? That's basically because things are moving perpendicular again to our line of sight, and so there is no Doppler information here. So that is basically the reason. So you might wonder by now, what are those spiral arms, and why is it that we see all the signs that we by now came to recognize as signs for star formation, like ionization nebulae, the reddish looking blobs, and then blue stars, right, which are massive, young, basically just produced stars. And then also the dark nebulae, which are a sign that there are molecular gas clouds, which is where stellar nurseries are located in those spiral arms. So we basically see that much of the star formation in the disk happens not just anywhere in the disk, but in the spiral arms. And we came to realize by observations and then some computer simulations that basically these spiral arms are waves of star formation, and they're waves in which the matter, the clouds of gas actually are smashing onto one another thanks to the, see here, there is a rotation of the galaxies. By the way, this is a real image of a different spiral galaxy. This is the so-called Whirlpool Galaxy. It's a pretty galaxy. So here's again the same image of the Whirlpool Galaxy. So here is in a nutshell what we think happens that produces these spiral arms, and that's and why we call them, we have increasing evidence for the fact that they are waves of star formation. So what happens again? We have, right, you see these arrows, they show also the direction in which the galaxy rotates around its axis. first of all, right, so we have gas actually gets squeezed as they move into spiral arms. They actually create those spiral arms. They follow the same orbits as stars and they become compressed as they enter the spiral arms. And then it is thanks to the squeezing of the clouds that the gravity, gets that boost, right? And winds, and that obviously triggers the star formation. The clouds of gas are going to contract under gravity and they're going to become really hot in the very center, and that's where the fusion of hydrogen to helium is going to proceed. And what's going to happen next, right? Because there is this kind of pushing, so gas is pushed and squeezed towards those spiral arms, right? Then young stars are going to flow out of the spiral arms. So you see how they're at the outer edge of those spiral arms. So here's some interesting things to note. The blue stars die away long before they complete one full orbit. And so they're basically, we only get to observe them, to catch them with our observations, only when they're very close to the spiral arms where they're actually born. While on the other hand, the red and yellow mass stars, right, like look at that, things like this, right? So you see yellow, white, so smaller mass stars, they have longer lives and so they survive for many orbits. And therefore populating the rest of the disk, basically the entire disk, okay? Now the star orbits are oval, just like this oval shown here, which are rotated slightly relative to their neighbors, and it's merely that slight rotation that allows for the squeezing of the, like you can imagine many ovals coming closer and closer and closer together, and they form that spiral arm model or a spiral arm feature that we see when we look at galaxies like this. Now, it turns out that discussing the basic properties of a galaxy, we actually get some really important clues to the history of our own galaxy. So we have already seen how the disorderly orbits of halo stars actually differ from the generally circular orbits of the disk stars, right? So this is the disk here. And then we have the halo. The halo. And then here's the disk, right? And you remember the stars in the disk, they kind of bob up and down, but then in the halo, they're randomly distributed, the orbits. So that's an important difference that we see between different types of stars. We also see another type of difference, the halo stars, right? The ones that orbit in kind of random directions. They don't have as many heavy elements, things that are different than hydrogen and helium, which suggests it was not much recycling of gas happening. So basically there were no cycles of star formation that happened before these halo stars were formed, right? We know of the disk stars, there is a factor of 10 or order of magnitude more heavier elements than hydrogen and helium, okay, which suggests, and we do see stars of all ages that form later and that they keep forming, as we've seen in the spiral arms. So another, quite important difference in what's happening with star formation and stars is properties of stars in general in the halo and then in the disk stars, and that actually can provide some really important clues as to maybe how this whole thing was put together, right? So again, halo, generally old low mass stars with a much smaller proportion of heavy elements than stars in the disk. So one idea, maybe the halo stars must have formed very early in the galaxy's history before the gas settled into a disk. So in order to accommodate these findings, these evidence that we have in these different properties of the stars, we came up with this Milky Way's formation scenario. Obviously, this is quite oversimplified, but the idea is the galaxy probably began as a huge blob of gas that we can call it a proto-galactic cloud. And that happened when the universe was less than 1 giga-year old. And then gravity caused the cloud to shrink in size, okay? And therefore potential energy is lost, or potential energy is converted into kinetic energy. Things become hotter in the very center, but also, right, in the meantime, there are some stars formed in the halo first, right, as gravity caused the cloud to contract. Now everything is going to be settled into a spinning disk. Everything, what I meant by everything was the remaining gas that was not by now locked in stars already formed in a halo. And that's where we see those things in the globular clusters of stars. All right. Now, remember the reason for which the remaining gas will settle into a spinning disk? That is the conservation of the angular momentum. Okay. So now we have the disk, and then stars obviously in the halo are going to be formed much earlier than stars that now start forming, because eventually the gas cools and starts forming stars in the disk. The clouds start collapsing under gravity, and so we end up today with stars continuously forming in the disk. There are some other older ones that have been formed, but also with other things that are older that must have formed before the disk was formed. And then, of course, there are detailed studies that might also suggest the idea that the halo stars formed actually in clumps that later merged. And we do actually have some very new evidence, like in the past 10 years or so, and it's people are actually studying this as we speak, that we see some streams of stars, some tidal streaks that appear in a halo of the Milky Way, and people are studying the ages of the stars in those streams, and their colors and properties, and these are ideas about we're actively trying to figure out how a galaxy like our own was put together. And then of course we study many other galaxies and compare what we find in other galaxies with what we observe in our own, and the models get better and better to accommodate all kinds of observations we get about them.